So, the actual subject for today is to get us started talking about one of these fundamental problems in networking, which Sylvia mentioned, which is routing. So sort of, setting the scene, the game plan for today. We'll see how this actually works. I'm going to start out sort of setting the scene with a quick disclaimer, a quick statement on addresses. Then I'll talk a little bit about what is a router. I'll talk a little bit about, why we have routers at all. I'm going to then sort of present like the challenge of routing and then the challenge of forwarding. Then I'm going to sort of compare and contrast the two of those. Then going to get a little bit into theory. We're going to talk about sort of a graph representation of routing. We're going to talk about this notion of routing validity, and then we will see how to actually use that notion of validity to validate routing state. And then we will probably end up with this in-class activity. So the disclaimer here is that there are about 1 billion ways to do routing. And I'm going to sort of constrain our initial discussion today to sort of like how the archetypal internet works. I'm going to make a lot of assumptions based on this. And next week we'll talk about some alternatives. So if you cast your mind back to the salad days of 2 weeks ago, we talked about packet headers. And we said that a packet header must contain a specific field. Does anyone remember what field we said packet header must contain? Yeah. The destination IP, or more generally a destination address. And so I think one can actually argue that you could build a network where this isn't true, but it's true for like every networking technology I could easily think of, and it's certainly true of the internet. And I'm not sure that we've outright stated this before, but this sort of implies that hosts have addresses. Thinking back to Sylvia's example with CEOs delivering letters, the CEOs had some address associated with them, like one infinite loop in Cupertino for Tim Cook, or one Hacker Way in Menlo Park for Mark Zuckerberg. And in fact, hosts might have more than one address. So why is that? Why might a host have more than one address? Yeah. What was the second part? Yeah. So anybody else have another reason? Yeah.
They have multiple servers, such as they need multiple addresses.
Multiple servers?
Yeah, multiple servers, like one in different locations to help people get better performance and stuff.
So I think you're onto something, though I might say it a little bit differently. And so the sort of two reasons, I think, if I'm interpreting kind of what you're getting at correctly. So one of them was that you might have different addresses for different layers, right? Like, your cell phone, right? Or just, any computer, might have like an Ethernet address, an L2 local address, and it might have an L3 IP address, a global address. So it might have, addresses at different layers. The other one is, I think what we were getting at over here, which is you might be connected to multiple networks, and you might have a different address on both of those networks. For example, your phone, you might be connected by Wi-Fi and by cellular, and each of those connections might have a different address. So for now, though, and for much of our discussion on routing, we'll be thinking a little bit more abstractly. So we'll just think of a host as having, a single sort of abstract address. We'll get into some sort of technical details of addressing next week. But for now, I'll probably draw hosts something like this, and say that a host drawn like this has the address F. So, moving on, let's ask a pretty basic question, which is, what is a router? There's a bunch of different ways to answer this question. Again, casting our minds back to lecture 1, we had a diagram that looked something like this. And it had this thing labeled switch on it. As Sylvia has talked about, when she and I say switch, we often mean that kind of interchangeably with router. And so this thing is a router. A router is sort of an intermediary node that usually connects to multiple neighbors. From a very different perspective, in this class, a router is often this. Sometimes it's this. We're probably not going to be 100% consistent, but it should be clear from the context. If you were to ask a network engineer what a router is, they might tell you that it's this. This is the schematic symbol that network engineers use to represent a router. Many of you, perhaps all of you, are familiar with this being a router, a home Wi-Fi router. This is also a router. This is a 24-port Cisco Catalyst. And this is a 96-port Cisco Catalyst. And so these two things are the kinds of things you might find somewhere in a campus network or maybe in a wiring closet somewhere. The previous one looks a lot like what a lot of what are called top-of-rack switches in data centers look like. And the big obvious distinction between these last two is the number of ports they have, right? Each of these little holes is a place where you can plug in a cable, or when we think about that logically, it's a place where a link can exist, right? So this one supports a lot more links than the previous one. Another note is that these last two in particular, a lot of people would tell you that these are a switch, but they do routing, so I'm going to say they are also a router. So again, the distinction between the two is not really all that clear. Another one, here's a thing called a Cisco CRS-1, and it's like it's called the carrier routing system. And this is the kind of thing that you might find in a major ISP. And so these things are big. This is, taller than I am. It can support many links, very high bandwidth links, and so on. So there are a lot of different kinds of actual routers. Again, in this class, to us, they're mostly just squares. So, any questions on those? So, moving on, we have this question like, why do we have routers at all? And maybe this ends up being obvious, but I thought we could sort of quickly just sort of think through a couple of the reasons. So, if you've got a couple hosts and you want to send data between them, it's pretty easy to just put a cable between them, and now A and B can directly communicate. If you've got more hosts, though, what are you going to do? You could sort of continue that same pattern and just put a link between every host, and now everybody can directly communicate with everybody else. So is there a problem with this? Yeah. It doesn't scale very well. Why not? Yeah, like every time you add something, there's a lot of work, right? Like there's a couple reasons you can think about why this doesn't scale, right? Like, for every host, like in the network, there's that many hosts minus one links that exist in that network, right? So, first of all, that doesn't probably scale to your home or your apartment, right? There's billions of devices on the internet. You probably don't have room for all the cable in your house. Also, anytime anybody added a new host, right, somebody would need to go to everybody's house and, hook up the new cable, right? So this obviously doesn't scale too well. And also, most of these links would probably be idle most of the time, right? Do you communicate with every single other host on the internet? Are there any positives to this sort of design, though? Yeah. Yeah, so connections are direct and low latency, and not just the latency, even more like the bandwidth, right? You've got dedicated bandwidth to everybody. So that's nice. Another thing is it's pretty robust, right? Like if this link between A and B fails, none of the other links are affected, right? All the other pairs of hosts can still communicate just fine. So if the scale is small and the need for your performance is great, this design might make sense. Another way you could think about doing it is something like this, where all the hosts are sharing like literally the same wire. So anything good or bad about this approach? Yeah.
Scales really well because all you have to do is add a little bit more wire to connect the host.
Yeah, so in some sense it scales really well, right? Like connecting a new host just means adding a little bit more wire. Anybody else? Anything good or bad about this approach? Yeah. Yeah, so in some sense it's not very robust, right? Like if this wire breaks anywhere, some of the hosts are going to get disconnected, potentially a lot. Any other thoughts, good or bad, about this approach? Yeah. Yeah, there could be a lot, like, as opposed to the other design where everybody had, sort of like reserved link to everybody else. Here, everybody is sharing the same link. Everybody's trying to fight for the same bandwidth. Right behind you? Did you have another? Same thing, okay. So, everybody's competing for the same bandwidth, maybe not very resistant to failures. We had one argument that it scales well because you could just add a little bit more wire to add another host. It also, you maybe would say, it doesn't scale to the size of the internet having just one giant wire that has to wrap around the Earth and visit every single person. So another good thing about it potentially is that maybe this is really cheap, right? It's just one wire. There's no extra nodes. There's no, forking of wires. So, again, there are cases where maybe this makes sense. Historically, a lot of local networks have worked like this. Ethernet traditionally worked like this. And so we may come back to this type of network a little bit in the future of this semester. But, here we can kind of see the benefits of adding intermediate nodes, these routers. First of all, you don't need an exponential number of links, right? You're also not trying to share a single link, so you've got sort of more bandwidth to go around. Like the traffic between A and C here doesn't affect the traffic between E and D at all. And if a link goes down, you may be able to find alternative paths. So this approach kind of solves some of those problems, and maybe you can see it as sort of like a nice middle ground. Any questions on this? All right, so now that we've talked about sort of the what and why of routers, let's start to dig into what I'll call the challenge of routing. So the basic challenge of routing is when a packet arrives at a router, how does the router know where to send it next such that it eventually gets to the intended destination? Like if A is trying to send a packet to B on this network, it's first going to arrive at this router R2. But should R2 send it to R1 or to R3? And when we make that sort of decision, we want to send the packets in a reasonable way, right? Using paths that are in some way good. And good could mean a lot of different things, depending on the context. It could mean the lowest price. It could mean the fastest. It could mean the most reliable. It could mean not using a competitor's network. In some examples on Thursday, we'll think of it as the fewest number of hops, in which case, a path like this between C and B, which would work, is not particularly good. And so this sort of takes some approaches off the board immediately. Like, imagine that routers know their neighboring hosts, but nothing else. So then what if a router, when it gets a packet, if the host isn't directly attached, what if it just forwarded it to another router at random, another neighboring router at random? Like, that would work, right? And it's really simple. And simple is good. But why wouldn't you want to implement routing that way? Yeah?
It might get into a
Well, okay, so it could get into a loop, but it's making a random decision every time. So would it be infinite? It's sort of probabilistically, Anybody else? Any other thoughts? Yeah.
We're wasting a lot of resources where if you actually implement proper patterns, then you don't have to keep sending things randomly back and forth.
Yeah. So it's wasteful, right? Like it's sending over links it doesn't need to, and just thinking about it, like how long will it take this packet to get to its destination if you just make a random choice at every step, right? Like who knows, right? It could take any amount of time. Similarly, you could have a router that just sent a packet to all of its neighbors. And if its neighbors, send it to all of their neighbors, and so on, with a caveat that we'll get to in a future lecture. That should work too, right? So why wouldn't we want to do that? Why not just send it to everybody? Yeah?
It congents the wires pretty quickly.
Yeah, so it's just super wasteful, right? You'd end up sending the packet over every link, no matter where it's going, and you could probably just send it over a subset of paths or of links, right? Meaning on a path. And so finally, another part of this challenge is we want our routing to be able to adapt to arbitrary topologies, because the graph that describes a network can vary a lot. For example, this is the topology of UUNet. UUNet was a carrier network, meaning that it's a communications provider. And specifically, it was what's called a Tier 1 provider. And I think we'll probably talk about more exactly what that means later in the semester. But sort of like the first order approximation, it means that they're like an ISP for ISPs. Today, they're part of Verizon. But you can see, there's a lot of links, kind of messy, gathered around major cities. CenturyLink is another big ISP, and this is kind of what their North American network looks like. Berkeley's network, a little bit more structured, looks something like this, with residence hall over there on the left. Various other things up at the top is how it connects to its ISPs. Enterprise networks kind of have their own thing going on. They often have like a head office and several branch offices. Data center networks often have these very regular structured topologies, something like this. These things are really engineered, and they're sort of, engineered without the constraints of, like geography and populations and so on. Of course, the internet as a whole is sort of a mishmash of everything, right? Because it's, like a network of all these networks. And so, in all these different networks, we might actually use different routing algorithms. But it's still generally good to have a routing algorithm able to adapt to any topology. And this is especially true because every topology is dynamic. They all change. And so why is that? When I say that every topology changes, why is that? Yeah? Any router can go down, right? You always have to deal with failures, right? Somebody could put a backhoe through a link, or the power could go out where a router is connected, anything like that, right? Another reason why, lots of networks are dynamic, because you might want to add equipment too, right? You might want to say, oh, well, we need more bandwidth here, so we're going to install new links. We have new customers, so, we're going to have to adapt to those customers and so on. But, everyone has to be dynamic because they all have to deal with failures. So, taking a step back from routing. Let's talk about one of the other challenges that routers face, and that's the challenge of forwarding. So when a packet arrives, for example, at R2, so a packet arrives at R2. R2 is going to forward it to one of its neighbors, right? It's going to resend it. And so you need to decide which neighbor are you going to resend that packet to. And you want to be able to make that decision fast. Remember, like, packets can arrive on the order of nanoseconds. So this sort of implies that whatever decision making that you need to do when a packet arrives needs to be really simple. And so almost universally, the solution to this is that these devices just use a simple table lookup. So here's a network. R2 might have a table that looks something like this down at the bottom. For every destination, there's a row. And in that row, there's a column telling it which neighbor to use to get to that next destination. That is, like, what the next hop is. For example, if R2 gets a packet for B or C, it's going to send it to R3. Any questions on this? All right. Now, at like a low level, right, eventually it's going to need to figure out like which physical port to send the packet out of, right? So maybe each port has a number, which I've sort of drawn up here. And then you can create a table that looks like this one on the right. There's sort of practical differences between these two, right? This one on the right, the second column is the port number to use. But logically, they're pretty much equivalent. It's a lot easier to do examples using ones like the ones on the left. So we'll often stick to that, but sort of be aware that both of these exist. So note that the only thing which determines our forwarding decision in this case is the value in the destination address field of the packet header and the value in the corresponding row of the table. Which is to say, if the tables are fixed, then only the destination field determines what happens to a packet. So we call that destination-based forwarding or destination-based routing. And it's kind of the most basic way of doing this. And it's super common. It's one of those sort of like archetypal internet things. And we'll talk about some alternative approaches later, but you should think of this as the default. So taking a step back, we'll look at the two things we know routers do, forwarding and routing. So forwarding looks at a packet's destination in the table and sends the packet to the neighbor given in the table. Routing, on the other hand, has routers communicating with other routers in order to determine how to populate that table that you're going to use for forwarding. That's how that table gets set up. So forwarding is inherently local, right? It only involves the arriving packet and the local table. And so, that is, if a packet for host B shows up at some router, all you need to do is look up B in the router's table, and you know where to forward the packet. Routing, on the other hand, is inherently global. In order to have figured out what R2's table entry for B should have been, you need to know something that's not local to R2, right? You need to know where B is, and B isn't local to R2. So Sylvia mentioned this term data plane a couple lectures ago. And so forwarding is the primary role of the router's data plane. When we talk about the router's data plane, we're primarily talking about forwarding. The primary role of the router's control plane is routing. That's the primary control plane operation, is figuring out these routes. And so finally, we can look at the timescales that these things operate on. And so forwarding takes place at the timescale of packet arrivals. So that might be as fast as on the order of nanoseconds. Routing generally takes place much slower, right? You only need to change these tables when something about your network changes. So that's something like when a link fails, or when a router fails, like we talked about, or when a router is added. So any questions on forwarding routing? comparisons between the two? Makes sense? Okay, so let's talk a little bit about theory. So we can graph the path that packets to a destination will take by if they follow the table entries. I've sort of been doing this all along, but one possible set of table entries for paths to A from R1 and R2 would look like these, right? From R1, it's going to follow this red path. From R2, it's going to follow this blue path. And so, the next hop entry in the table becomes an arrow in this graph. Notice that, because there's only one next hop per destination in those tables, there can be only one outgoing arrow per node if we're looking at it for a specific destination. And so that means, once paths meet, they're never going to split. Like here, you can see sort of two different places the paths could meet depending on what the table entries look like. So in the top, paths to A from R1 and R2 don't meet until R8. In the bottom, they meet at R4. But in either case, once those two paths to A meet, they're not going to diverge again because there's only one next hop for packets going to A. So like in the bottom, it's not like one of the paths could go from R4 to R6 and the other could go to R8, right? They both need to follow the same wherever it goes. Does that make sense? All right, so the set of all paths to a destination form this directed delivery tree for that destination. And this tree, has to cover every node. We want to make this assumption that a packet to somewhere can arrive at any router and will have a way to get to the destination. And so, technically speaking, this creates this oriented spanning tree rooted at the destination, meaning it's a spanning tree with directed edges which all point towards the root. A spanning tree is a new term to you. A spanning tree is a subgraph that touches every node in the original graph and forms a tree. That is, it doesn't have any cycles in it. Any questions on this? All right, so moving on. Earlier I said that, we wanted good paths between hosts. And the notion of goodness is flexible, but surely the minimum requirement for good must be that packets eventually reach their destinations, right? Anything else is definitely not good. So it'd be, useful to be able to reason about this. And this was articulated by Scott Schenker, who is my advisor, as routing state validity. And this is a term that we use at Berkeley. It's not a standard term, but it's a useful one. And so in order to discuss routing state validity, we need to distinguish between two different views of state. And so the local routing state is just the contents of a table at any particular router. By itself, this can't be evaluated for its validity. It needs to be evaluated in terms of the global context. And so all that's saying is, if I give you some router's table, here's R2's table, is that valid? Will packets forwarded using this table get to their destination? Obviously, there's no way of knowing from just this information, right? So the global state is the collection of all the local state. It's, the contents of all the tables across all the routers. And so this is what actually determines, which paths packets take across the entire network. And we say that the global state is valid if it produces forwarding decisions that always deliver packets. So we can think about the goal of routing protocols as computing valid state. And eventually we're going to talk about how you actually do that. But just assuming that you've got some routing state, how can you tell if it's valid? we want a succinct correctness condition for routing. So I'm going to give you a second to think about, what makes routing correct or incorrect, and then I'll ask all of you what you think. So take a minute, think about it, talk about it with the people next to you if you like, and what is the clearest way to define correct routing?
How do you tell if it works? It works. So, test it by sending a packet from everywhere it's coming from. Well, that's the problem. The problem is that that's hard to do, right? Is there a better way of finding out? Just sending a packet from everywhere to everywhere.
Give you a few more seconds. All right. Anybody want to volunteer something they come up with? Anyone have an idea? Too early in the morning to be daring? All right. So I'll tell you how Scott articulated it. To foreshadow things, it turns out that for destination-based forwarding, this is the same as saying that your graph should form this, delivery tree that we talked about earlier. To see why Scott, at least I think it was Scott who formalized this, came up with this theorem, which is a single necessary and sufficient condition for validity. And so basically it says that the global routing state is valid if and only if, for all destinations, there are no dead ends and there are no loops. So a dead end is when there's no next hop somewhere. Like if a packet arrives and it's not forwarded, because there's no table entry for it. Note that the destination doesn't forward the packet, but we don't count that as a dead end because it's the destination. That's the good thing. Other hosts are also generally going to act as dead ends because generally hosts don't forward packets. Make sense? A loop is when a packet cycles around the same set of nodes. Since forwarding is deterministic and it's only depending on the destination address, if this ever happens where it gets caught in this loop, it's just going to stay in that basically indefinitely, right? So let's see if we can prove that this is the case. Starting with the necessary part. Yeah? Yes, if there's a power outage, then that could change things, but a power outage you can consider as being a dead end, right? It's going to, try to send it to the one where the power's gone out, and that's going to be a dead end. So, and this is looking at sort of, from this sort of theoretical perspective. So, I would say I would map your practical example of the power goes out and some router dies as being a dead end. Does that make sense? Okay, so the necessary part is pretty straightforward, and it's basically saying, that for state to be valid, it's necessary that there be no loops or dead ends. An equivalent statement, if you do some logic to it, I believe this is the contrapositive, says that if there are loops or dead ends, the packet won't reach the destination. And so, we can sort of show this, if you hit a dead end before hitting the destination, then you're never going to reach the destination. Obviously, right? Similarly, if a packet gets caught in a loop, because you're just going to keep looping, right? Because it's deterministic and it's only based on the destination address, which doesn't change. If you get in a loop, you're going to stay in a loop. So that's also not going to get to the destination, right? We know that the destination isn't on that loop, because if it was, it wouldn't have looped in the first place, right? It would have delivered it to the destination and then stopped. So, therefore it's necessary that there be no dead ends and there be no loops. That makes sense? Okay, so the other part is this sufficient part, which is a bit more tricky. Right? And so the sufficient part says that if there are no loops or dead ends, that's sufficient to know that the state is valid. That's sufficient to know that the packet will be delivered. And so proving this, it's a bit more subtle, but assume that the routing state has no loops and has no dead ends. So therefore we know that the packet can't hit the same node more than once, right? It can't hit it twice, because that would be a loop, and I just said assume there are no loops. Similarly, we know that a packet can't stop before hitting the destination, because I said there were no dead ends, right? So that's violating this other assumption that we made. And so what's left? What's left is that a packet has to just sort of keep wandering the network, hitting different nodes. Right? Can't hit the same one because that's a loop. So it has to just kind of keep hitting different nodes. But there's only a finite number of unique nodes in the network, right? So eventually, it's going to have to hit the destination node. So therefore, if there are no loops and no dead ends, then the routing state is valid. Does that make sense? So that sort of, showed that, this simple statement of the routing state is valid if there are no loops, no dead ends. We've sort of proven that at this point, and that tells you when packets will be delivered. So I thought now, let's see. Yeah, we've got time. So let's take a quick break, and we'll resume in maybe 5 minutes, something like that. I mean, okay. So let's get back to it. Assuming my clicker will continue working. All right, so putting it to use, verifying routing state validity. So now we've got this sort of, simple condition to check validity. So how do we use it? A couple notes first. First of all, hosts generally do not participate in routing. In the common case, hosts have just like a single link to a single router. And so they have this default route that sends everything to that router, unless they're the destination, in which case they don't send it at all. So they're not very interesting. So, we often ignore them except as destinations. Routers might be legal destinations, not just hosts, or in addition to hosts. This sort of depends on the design of your network, of your networking protocol. In Internet protocol, IP routers can be destinations, but how often have you ever wanted to communicate directly with a particular router, right? Quite probably never. So, host-to-host communication is certainly by far more common. And so we're often going to ignore the routers as destinations. But you do want to think about routers, any router, every router, as potentially being a source for packets sent to every destination, because packets may arrive at a router in sort of unexpected ways. Does that make sense? All right. So, putting our theorem to use here, we're going to focus on a single destination. We're going to ignore all the other hosts. We're going to assume all of the other routing state, except the routing state to that destination. And of course, we can do this, right, because they're all completely independent, right? I mean, it's only dependent on your destination address, and the destination address doesn't change. So if your destination address is, E, then only table entries for E matter to you. You can throw away all the other ones when you're considering this. So for each router, you're going to mark the outgoing edge with an arrow pointing at the next hop. Again, there can be only one outgoing edge at each node because we're doing this destination-based. Then eliminate all of the links with no arrows. And look at what's left. The state is valid if and only if the remaining graph is a directed delivery tree, which doesn't have any loops, right? And which all points to the destination. So remember, it's a spanning tree where the root is, where all the links point towards the root. All right, so checking the validity of the state to A. We've got this topology. We got A here in the bottom right corner. So we're going to ignore all the other hosts. And then we're going to, point at the next hop. So, you might have table entries that describe these arrows. You're going to remove the unused links. And is this valid? Who thinks it's valid? Quite a few. And so, yeah, this is valid, right? It's a spanning tree converging on A, rooted at A. Right? It touches every node. All the arrows point towards A. So here's a second example. You might have forwarding state table entries that describe these arrows. And so you remove the edges. And is this one valid? Anybody want to say why they think it is or is not valid?
No, because it's not a tree.
It's not a tree, right? And in the terminology of our theorem, it is a forest. You're right. In the terminology of our theorem, what's wrong here? Yeah. There's a dead end, right? This is a dead end. It doesn't have an outgoing arrow. So here's another one. We remove the links that don't have arrows, and you get this. So is this valid? Anybody want to volunteer? Yeah.
It's not valid.
It's not valid, right? Because there's a loop, right? All these arrows just kind of point to each other. So what about now? Yeah. There's a dead end, right? It looks a lot the same, except now this node's a dead end. It doesn't have an outgoing edge. What about now? Valid? Not valid? Anyone? Yeah. So, does it have a dead end? Even more fundamentally, it's got a problem. This node has 2 outgoing edges, right? That's not even possible with destination-based forwarding, right? You only got one next hop. So this one can't even happen. How about this? A final example. Is this one valid? No? Why not? Because that one? Yeah, it's got a dead end. Can you fix this one? Or how could you fix this one? Yeah, in fact, if it had forwarding state to any of its neighbors, any of them would actually work in this case, right? It would create a directed arrow from that dead end to any of its adjacent routers. Any of those would make valid forwarding state. So, kind of summing this up, it's really easy to check the validity of routing state to a particular destination, right? The dead ends are obvious. You end up with a node, with no outgoing edge. So obviously that's not going to be able to reach the destination. And loops are obvious because they end up disconnected from the destination and disconnected from the whole rest of the network. So now you just need to repeat this same process for every destination. And that tells you whether your entire global state is valid. Does that make sense? Anybody, any questions on validity? Okay. So a final note on validity is that we've been looking at this from the perspective of destination-based routing. This same basic rule of no loops, no dead ends generalizes to at least any other system that does deterministic forwarding based on fixed packet headers. That is, it's not necessarily limited to just destination-based routing. It may generalize beyond that. I haven't thought about it hard enough to figure out exactly where that stops working. Maybe Scott has. But with just a little addition, which we will, I think, talk about next week when we talk about sort of broadening beyond just destination-based, with just a little addition and carefully considering what actually constitutes a loop, this generalizes. And so now, unless anybody has any questions, I'm going to move on to something completely different. We're going to try this activity. It may work, it may not. We'll find out. And so here are the rules. We're all going to work together. You are going to talk with your neighbors, that is, the people to your left and right and in front and behind you. I realize you're not exactly aligned, so kind of figure out who you think is in front and who's behind, who your neighbors are. And some of you obviously won't have neighbors on all sides. Hopefully you have neighbors on at least one side, probably by definition. And so everybody is going to have a magic number, your own personal magic number. Everybody's magic number initially is infinity. you would like to have a magic number that is as low as possible. You want to be number one. And so if your neighbor ever offers you a lower number than your current number, then that's now going to be your magic number, right? A neighbor is going to give it to you. And so when that happens, you should immediately offer your magic number plus 1 to your neighbors. Remember, you want to be as low as possible, so you're going to give your neighbors 1 more than you have, right? So try, remember your magic number, certainly. Try to remember who gave you that number. And so if somebody offers you, the same number that you already have, or offers you a greater number, you ignore it. So I've written this up in sort of words, and I've written it up in sort of, basically Python. And so take a second to look. Is everybody clear on what the rules are, on what to do? Yeah.
How do we ever get lower?
Don't worry about it. I mean, your neighbor, you're starting with infinity, right? If anything your neighbor gives you is going to be better than that, right? So don't worry about that. If your neighbor gives you a lower number, that's your number. Everybody clear on what the algorithm they're implementing here is? All right, so with that, let the game begin. Everybody do this. We will reconverge in a few minutes. So remember, as soon as your neighbor gives you a better number, you want to immediately pass it on to your immediate neighbors, right? Everybody doing that? Keep going. Gonna give it a couple more minutes here. Anybody have a number greater than 50? Anybody have a number greater than 1,000? Interesting. Anybody have a number greater than 2,000? Interesting. Okay. Give you 30 more seconds. Remember the algorithm. You want the lowest number that any of your neighbors has offered you. You should offer that your number plus 1 to all your neighbors. All right. So, remember your number. So let's do the second part of this. Let's talk about your best friend. You wanted a low number. Your best friend is the person who gave you your number. So, note that you are never your best friend's best friend. I'm sorry, life is unfair. So, if you forgot who gave you your number, you forgot your best friend. A, you're terrible, and B, it's easy enough to figure out, right? At least one of your neighbors must have your number minus 1, right? So pick any of those people, and that person is now going to be your best friend. Is that clear to everybody? Who your best friend is? Okay. So now, TAs have envelopes. Some of them. Those TAs are going to give one of their neighbors an envelope, and you give that envelope as a gift to your best friend. All right? Everybody clear what we're doing? If you get an envelope, pass it to your best friend. Okay, go.
Oh, wait. Oh, sorry. Where did you get his number from? All right. What was your number? 5? Oh, we got a horde of it. You got the one. There's an envelope up there. We have some copies there. We got two up. Let's go ahead. Take it.
So someone gave you your gave you your number, right? That person must have less than yours, one less than yours. You're going to pass it to them.
Shuffle around. I don't know what's going on.
All right, got a little bit less than 1 minute. Remember, if you've got a number, pass it to whoever had the least. All right, we're going to call it. So, with any luck, some envelopes got to their destination. I think there were 5. I think there might have been 4. So, who has an envelope? One over there? One over there? How many do you have? 2? Anybody else? Okay, so I think there were 4. Okay, and so, why don't you open up your envelope? What does it say? It says, "Hi, Ian." Are you Ian? That's too bad. Someone else open one up. Are you Ian? That's too bad. How about you? You got 2, right?
Yes.
And what do they say?
And the other one also. Hi, Ian.
Are you Ian?
Yes.
Ah, okay. So we worked 50% of the time. So, how did this work in the cases that it worked? We'll think about why it didn't work in a minute here. What happened? So, everybody started with infinity. So this is y'all, these black boxes here with infinity in them. Ian started with 0. Ian told his neighbors 1. His neighbors told their neighbors 2. And so on. Right? And so it created this sort of slope leading to Ian. And so then from wherever, at least from 2 places, we started envelopes moving, right? And just sort of handed them down this slope, and they ended up at Ian. So, everyone who passed an envelope, raise your hand. So, here's an obvious path to Ian. And, there's another path to Ian. And so those are part of this, this delivery tree leading to Ian. So this generalizes this same basic approach to many destinations, right? All we need to do is keep a separate number per each destination, right? You could have kept your Ian number and your Sylvia number and so on, right? And this would have generalized to everybody. Any questions on this basic algorithm? Yeah. What's that? Oh, I didn't. I gave them to Ian. Ian is one of the TAs. Good guess, or good question. Yeah, any other questions?
Oh,
Yeah.
If we have two destinations, then how would we make sure that the right will get to the right destination?
Yeah, so we would have written, in that case, you would have written Ian on it, right? And you would have said, okay, so my Ian number was given to me by this neighbor. My Sylvia number was given to me by this neighbor. So, yeah. Other questions? Yeah.
Wait, what if we keep track of a lot, but there are a lot of number of destinations in the network. How do we keep track of all of them?
Yeah. So how would you keep track of it if you had a bunch of different ones? Maybe in a table, right? It's one per destination, right? Well, we could talk about,
Is it reasonable to keep track of everything?
Anybody? Is it reasonable to keep track of, an entry for each destination on the internet? Is that reasonable? Maybe not. What about for each destination at Berkeley? Maybe, right? So maybe it depends on the network, right? And so we'll talk about, in a later lecture, how you can sort of deal with that. Good question. Okay, so what could possibly go wrong? What did go wrong? Anybody have any thoughts about what could go wrong here? Yeah. Some people maybe just didn't say their number to their neighbors. Yeah.
There's seating gaps, so there's not necessarily a way to.
Yeah, there's kind of gaps, right? Did they consider someone their neighbor if, there was nobody next to them? Anyone else? Yeah.
Some people made up numbers.
Maybe some people made up numbers, right? Any other thoughts?
That's good.
All right, so I wrote some down. We covered some of them. So sitting too far apart, right? We got that one. And so that's a network partition, right? You didn't have any neighbors. You may have forgotten your magic number, in which case that's like a router failure or maybe a router rebooting, right? You may have misremembered or misupdated your magic number. And that's sort of the equivalent of an implementation bug, right? I think I heard one of these may have happened somewhere over here. Maybe a neighbor didn't hear the update, right? These networks, they're best effort, right? They're not reliable. So maybe your neighbor just didn't hear you, and so that's like a packet being dropped. Maybe you exchanged magic numbers, right? And a neighbor gave you the number. They should have been your best friend, but then they left. Right? Peace. So that could cause a problem, right? If that person leaves. And so that's like a link failure, right? And then we got this one too. Someone might have lied about their number. You might have had a malicious actor, right? An attacker trying to subvert your network. So, there are a number of things that could go wrong. We probably got a number of these going on here. We lost two packets, 50% packet drop rate. That's not too good, but, it's an early version of this network. So I think we probably had a partition. And so anyway, what we implemented here is this distributed and asynchronous version of the Bellman-Ford pathfinding algorithm. This should maybe be called the Schimbel-Ford-Moore-Bellman algorithm if you took all the people who published the same algorithm in the order of publication. That's pretty long. It's usually just called Bellman-Ford. And so if there's a couple things that we know about networks, right? Networks are distributed. They've got many independent components. And we also know that networks are asynchronous, right? All the things don't operate in sync. It's not like if you do Bellman-Ford on paper and you can do every step in exactly the right order. You are all sort of doing all the steps all at once in sort of arbitrary orders. But this algorithm works anyway. So this seems like a really promising algorithm to turn into a routing protocol. And in fact, that's exactly what we're going to do on Thursday. That is exactly what you will do for the project. And so in the final few minutes here, I thought I'd just say a little bit about distance vector protocols in general. And so, yes, a lot of text. So, routing protocols that implement this Bellman-Ford style algorithm are called distance vector protocols. Adjacent routers conceptually are exchanging a vector that is an array, that version, the linear algebra version of vector. They're exchanging a vector of distances with their neighbors, right? Because it's not just one number like you did. It's, a vector of numbers. It's your Ian number, your Sylvia network, your James number, and so on and so on. And so really it seems more like it's like a vector of tuples, or it's like a map of distances, like destination to distance, but that's what you're exchanging. This distance vector type routing protocols were used in ARPANET, which was the predecessor of the internet, as early as like 1969. So they've got pretty long history of routing in the internet. Later they were implemented by Xerox, who we all know from copy machines, but Xerox was really quite influential in networking and a lot of technologies for a while. And then it was implemented by this thing, routd, that is the routing daemon of BSD Unix, Berkeley Unix, in 1983. That version of the protocol was then, basically standardized in 1988. It's been updated a couple times, one to support classless addressing, which is something that we're going to talk about next week. It was updated to work with IP version 6, which is something that we'll talk a little bit about. And that protocol that comes from routd, which is called RIP, or the Routing Information Protocol, is sort of like the prototypical distance vector protocol. So that's kind of what our discussion of distance vector is going to center around, something very much inspired by RIP. The project, you're going to be implementing something very much inspired by RIP. Final note is, distance vector has been deployed historically quite widely. It's not nearly as common today, but it's also not dead. Cisco has this protocol, EIGRP, which is a distance vector protocol. It's used by a lot of Cisco networking routers. It goes back to the 90s, but it was only fairly recently opened up and standardized in these RFCs, which are sort of where the body of knowledge that makes up the internet is sort of codified. And then there are some other ones like this one, Babel, which was published as an experimental RFC in 2011, but it's still actively worked on. They're actually working towards a standard of this new distance vector protocol, Babel. But again, our discussion of it is going to go pretty much back to this sort of prototypical example of RIP. And so with that, finish up, and see you Thursday. We'll talk about distance vector in excruciating detail.
That's a really